Hello, this is Eric Frederick, the Director of Technology for Architects Inc., and today we're going to discuss how to perform particle tracking in ProAnalyst. We'll start with an overview of particle tracking application examples in different markets. We will then discuss the issues faced when trying to track particles using traditional camera systems, as well as ways to capture the scene in such a way that we reduce these problems. Then we will show 3 videos from customers who use ProAnalyst for their particle tracking research. We will briefly introduce ProAnalyst and the particle tracking toolkit, as well as the tools required to optimize your particle tracking data. There are also 3 common problems that customers encounter when using this toolkit, so we'll discuss these issues and provide several different solutions for all of them. As you may know, there are usually more than one way to solve a problem with ProAnalyst. If there is time, we'll finish up by analyzing a customer's video and opening the webinar for questions. Particle tracking is important in a number of areas. This toolkit was first introduced for basic research applications, and many of the features were added while working with a researcher on sea anemone feeding behavior. The pharmaceutical industry uses particle tracking for drug delivery and could use it to monitor pills on a conveyor belt as well. Chemical companies like spray paint manufacturers adjust the chemical makeup of their paint and see how those changes affect the spray distribution. Similarly, nozzle design manufacturers change the shape of spray nozzles and assess how those changes affect the overall flow and distribution. Agricultural companies are interested in tracking grains in a flow or crop spray distribution. There is also a great deal of interest to track bubbles and assess bubble formation, which is important for food and beverage producers. And of course, there are applications for military as well to characterize shrapnel patterns. So there are several issues that can occur when performing particle tracking in ProAnalyst. Particle tracking in ProAnalyst is performed using 2D captures of particle distributions with a traditional camera system. And when this is done, particles can cross in 2D or 3D space, and they can also merge together or break off one another. The particles can travel in and out of the focal or calibration plane, which is also a feature that's in ProAnalyst, where you can calibrate your field of view for a given setup. The particle intensity is not necessarily uniform over the objects either, and the particle can change its shape as it moves through the field of interest. And there may be also other boundaries or obstacles that can affect the flow and distribution. And there are, of course, other considerations that may come up on a case-by-case basis. One of the first items that we review with customers is their choice of camera lens. The choice of camera lens may not solve many of the problems presented on the previous slide, but it is a good place to start, as it can increase or decrease the amount of light and affect the depth of view. The primary goal of proper lighting is to achieve bright particles on a dark background or dark particles on a bright background. The latter case is what is achieved with backlighting, where the particles appear as moving shadows. A laser light will have the opposite effect, with particles being brightly lit against a dark background. In other situations, a light diffuser may also help, as it will even out the light intensity across the scene. Polarizing light filters can also be used to manage light reflections off the particles, so you can either enhance or de-enhance those reflections off those light reflections off the particles. You can also constrain the motion, but this may have other impacts that are undesirable for experiments. In this movie, this is the sea anemone movie that we have from one of our first customers for particle tracking. So here you see the sea anemone in the bottom, and the brightly lit particles at the top that are moving over and across the sea anemone are the food particles. In this example, we have particles flowing down a channel. And here we have a classic spray paint example where some jet or nozzle is firing or spraying the particulates across the scene, and the camera is capturing the distribution of particles. So if you're not familiar with ProAnalyst, what you'll find is when you first load a video, you'll have a right menu group, as you can see here with the red box and the red arrow. These have about 16 options, which can be a little bit of intimidating when you first look at all of them. But we're going to focus on 4 of them: the image processing button here at the top, the image filtering button, the particle tracking button, and the graph configuration. So we'll first start with particle tracking by activating it and clicking the enable or disable button to make that toolkit active. What you see in this window or in this dialog is you see the particle tracking buttons here, and they are shown as stepping buttons as well as rewind or forward buttons. The center button is used to just calculate the parameters for the scene shown or for the current frame. We also have playback controls, which allow you to stop, step forward, step backwards, or play forwards and play backwards, as well as go to the end of the movie or the beginning of the movie. These allow you to adjust the particle tracking parameters in real time. So you might run your particle tracking analysis, and during a QC review, you might find that maybe the particle tracks weren't recorded the way you want them to. So then you would step through with the playback controls, go to the frame where you first see a problem with your data. You can make some changes to the settings and then retrack, maybe even just do a single frame at a time, or just that one scene, and evaluate and confirm that it is working. And you can do this frame by frame, which is really useful from a quality control standpoint. If you're not familiar with particle tracking and with the toolkit in general, we have several algorithms which are used for the tracking toolkit. We have an 4-point connectivity search algorithm as well as an 8-point connectivity search algorithm. The 4-point algorithm relies on looks at the particle's motion and considers that it can go only to the 4 adjacent pixels, while the 8 connectivity algorithm looks at the 8 adjacent pixels, so it considers diagonal motion in addition to just translation vertically or horizontally. For the software, we've used -1 as a wildcard, so just use it with care and just be aware of it. It has some flexibility when you're doing these types of analysis. The correspondence, what we mean by that is that the software finds the particles within a given frame, and the correspondence considers how each particle has moved throughout all of the frames. So we might count, in this example, 4 particles in the scene, but the correspondent assigns a 1 through 4 of them, and then it needs to go through maybe 1 in 400 particles throughout the entire video. So that's what we mean by correspondence, is just how it corresponds between frames. Does the particles number correspond with the current particle that we're seeing? And then we also have a button called the recalculate particle numbers. And if you've used previous versions of ProAnalyst, you might not be familiar with these buttons because they were hidden in a right-click menu. But with the most recently released, we're going to have these available as buttons, as you see here, so you can quickly access them and see them. And this way, customers aren't confused trying to find these parameters. The particle correspondence settings is a allows you to adjust the algorithm. And as I've said before, it's frame by frame. So you can adjust how the algorithm considers the maximum distance that a particle moves. You can also adjust the weighting. So if you want to have a larger weight on distance such that the algorithm doesn't allow large leaps, it only considers small particle movements, you can edit that here, and that will allow you to adjust it frame by frame. Same thing with the angle that's moved. So if in this case here that you see, you have these particles that are falling down and they're striking this white surface, and they'll change directions. And so you might want a higher value depending on your situation. That way you can account for them being deflected off this lower bright region. Now, a common problem that people have is when they're analyzing their data, they might see that the correspondence trail is swapped. So this is a case where you have particle 13 and particle 15, and these orange lines represents the particle's motion throughout the video so far. So particle 13 was along that orange trail, and then suddenly at this frame, the software assigned it as being over here, which is clearly, from our understanding, is where particle 15 should be. So it's incorrectly determining where those particles should be. And you can correct for this in the software by adjusting the correspondences. And the easiest way to do this would be to reduce the max distance that the particles can move. And once you change that in this particle correspondence dialog, on the previous frame we see that the distance was 0.1, and on this current frame it is now at 0.5, and the problem is resolved. So the software, by increasing that value from 0.1 to 0.5, we're able to separate those two particles as two separate trails and two separate particles so that they don't get crossed. Another common problem is, in this case, we have our particles falling down and striking this white surface, and we have these purple arrows denoting the path of the particles over time. And here what we see is this particle hitting that boundary, and those arrows don't connect with the ones that are rebounding off the surface. So the particle comes down, and the software detects it as basically being a new particle now moving upward and to the left. So we want to correct that with the software. And for this example, what we did is we defined an ROI such that the algorithm's only looking at this space above that white plane. The other solution is to go to the filter, image filter toolkit, and apply a zero border filter. And this way you can eliminate that white boundary at the bottom. Okay, so there are multiple ways to solve this problem. All have their strengths and weaknesses. Another common problem is someone has this macroscopic behavior and they want to pull out microscopic information and maybe understand the properties of a single particle in their data set. So one way to do that is to go to the graph configuration, and here you can actually plot the macroscopic information. So we've done that here, where we've added a graph line for the average speed of all of the particles, and that's what we have. It's the average speed, so there's no direction associated with that. We will be adding the x and y velocity, so you can understand the average x and y velocity of all your particles in the scene, rather than just understanding the average speed of your particles. So now that you've added at least the average particle speed to your graph, you can then go up to the 2D tracking toolkit, which is this 2D button here, and you can create a new feature in that 2D particle tracking toolkit and set the feature to have a virtual point equal to the correspondence trail of interest. So if you're interested in tracking particle 13, you would just go into the 2D toolkit and create a feature and associate that feature with the correspondence trail of 13. And then you can go back into this graphing configuration module or toolkit and plot the x and y velocity of that single particle. And that's what we've done here. We have the average speed of all of the particles, the macroscopic information, and now we have the individual particle information in orange and green. And as you do this, you might want to change some of the layout. So we changed the color to orange by clicking on this orange dot. And we can also apply a filter to the data because maybe we want to smooth out this discontinuity here where the particle strikes the boundary, or maybe we want to smooth out the spike where it happens as well. You can do that on the filter button right there. Or you can just leave it alone. But you have more information about virtual points and what you can do with them on this virtual points webinar that we did several weeks ago. Okay, so now let's go to our real world example. Okay, this is a video that was sent in to us by one of our customers, and what you see on the left hand side of the video is a snail proboscis which is going into a boundary, some either tissue or something, and what will happen is a spear like projectile will shoot out of the proboscis and inject venom into the host is the idea. And the customer's interest for this project was to measure and quantify the distribution of particles that are being injected into the host in the spray-like fashion. So we initially go from a starting phase which was very chaotic and now into more linear stream-like scenario. We'll just reset it back to the beginning and we'll start to process it. So first we'll just adjust the brightness and contrast levels so we get pretty good contrast for the particles, and I'm just going to get it onto a frame so I can see the particles themselves. And I can adjust them lighter or darker accordingly, and we can see that there's a bright outline with the center region which is lighter than the boundary, and that does cause a little bit of problems with the analysis, but we can handle that as well with some filtering. And as we adjust this, we can go back and look at the raw images so we can kind of get a comparison of what we've done to what it used to look like. On the left hand side, those little tabs that are labeled processed and raw. And now we'll go to the image filtering. Everything's laid out in an orderly fashion such that you progress from the top down to the bottom. And what I'm going to add here is I'm just going to add a binary mask threshold. That takes all of my black and white information and makes it all either black or white. That way there's no more gray information in my data. And if I look at this, I can scroll through and I can see some holes in my particles which are also not desirable, so I'll add another filter, which is the Fill Center of Objects filter. And this sometimes has some issues where here we're seeing that it's causing the particles to disappear. So I'm going to change these and see if it's partly due to the levels. So for this binary thresholding filter, we have RGB, which is supposed to stand for red, green, and blue channels, but we are working with black and white images, so that's not really relevant with this data. So even if I change this to 160, it has no impact on the video itself. So for the black and white videos, it should only be the red channel that will really have an impact on your data. Okay, we can see what it's doing. And I'm just trying to get back these particles that I lost. And there's no other settings that I can do, but I can just simply, I'll look into why that happened, but I can just simply try to do this as well and see if that brings it back, but I don't think it will. I can also just remove it and get it back. For some reason it's eliminating the object, so what I'm going to do is I'm just going to reload what I did previously. It's a way to handle this, and it's difficult with this data because it does require a bit of time to get everything just right, and there can be issues at times. So this is the easiest, and I can look now and see how everything looks. Everything looks pretty good. So that might just be a setting that I'm not aware of, but by pulling up what I saved, I can go back from where I came from. Now we'll start to do the particle tracking toolkit. So we'll click it. It's currently enabled, so I don't need to enable it or disable it. And here what we see is that we have incentricity factor. In previous versions of ProAnalyst, this was the incentricity, but a customer sent us an email asking us about that because the incentricity is supposed to be a bounded value between 0 and 1, and the value that the software has reported is not bounded between 0 and 1. It was actually bounded from between 1 and infinity, which when we looked into the code and saw what was being done, we realized it was actually just what we're going to call an eccentricity factor, which is the major over the minor axis all squared, that whole ratio squared. And there will be a note, and we're going to add some more information so that this is pretty transparent for customers going forward. So that's one aspect. And we can see that we have the -1 flag here for the maximum eccentricity, as well as the max pixel area. This way we're going to capture all of the particles that we want. We will now define a region of interest. So we'll just click that checkbox and we'll define it. So we can first draw from left to right a box. Once that box is set, we can now move it around slightly to get it to be where we want it. And then we can set it and fix it in the field. Once that's done, we can set everything back to the beginning. We can do another comparison of just what we see and do a few more checks here of what we see versus what we're getting. Okay, and there's always going to be some give and take between getting all the information that you want, like these dark specks in the background, versus what you're actually going to measure. So it's tricky, and you have to kind of work with that. And just if you are missing something, then you have to rely on the power of statistics and get more data to get an accurate, or to get closer to average results. So we'll just start the tracking module and track through. We can also adjust the playback such that we look at a fixed part of our playback. That way we're not waiting forever for the particle tracking to go. So I'll just hit play. I'll just pause it so we can get an idea of what's going on. So what we see here is we see one object, which drawing a rectangular circle around it, so we can get an approximate idea of its size. We see this circle, which denotes the centroid. In previous versions of the software, it was called the center of mass, but that's not really an accurate way to say it, because center of mass could mean that it's a weighted intensity versus an unweighted intensity, but the centroid is a very specific term that captures what we're talking about when we're talking about the centroid of an object, which is an unweighted center, purely based on the distributions of pixels of that object. Okay, we also have the angle of rotation of the object. So we can see that this is at an angle of minus 3.4 degrees, and the eccentricity factor is 240 or 250-ish, okay, versus the other particles, which are much smaller in size, and the eccentricity values are very different. This one's close to 1, which means that it's close to being a circle. Here we can see the correspondence settings if we want to adjust them. Not much has changed from the previous version to the current version. It's just now we have a button so we can access these settings. And we can also recalculate the particle numbers. And once we've done that, we can look at the correspondences of all frames. So this shows us the correspondence for all the frames and how those particles have moved. We can also look at the correspondences of the current frame, which this shows basically the velocity from one frame to the next frame for this center of this centroid of our object. So we see that this object, the centroid for this object, has moved that much between the two frames. These were hidden previously in a right-click menu here under particle tracking for show correspondence current all frames, and we can also look at the particle trails. So this draws the particle trails of our particles. So we have 1 through 20 particles right now displayed. If we go back a little ways, we can step back and see, maybe see additional particle trails. 14 and 17 are also now shown. So and if we don't want to see the labels, we can deselect all of them, and that way we only see the major and minor axes of the objects, or not. It's better usually to keep these hidden from view, and that way things can draw a little bit faster because there'll be less processing to do, but it is nice to see them as it's going through each of the frames, either the bounds or the particle outlines. We'll just keep the particle boundaries. Okay, and if we just go forward and continue on with this, we'll wait till it gets most of the way done, at least for our little bit that we want to analyze. And this particle that's kind of moving and coming to a stop in the center, we could actually put a filter there to limit it if we want it, but we'll keep it. And I'll stop it so we don't waste too much time on this. Now, if you want to export your data to Excel, there is the option here at the bottom, and we'll export it. You can see that it's saying exporting to Excel. It's going to take some time because it's a pretty large amount of information in this file. And here I can see it in the background. Okay, so here are my particles. I see particle 1, 2, and as I scroll down here, I can see that it's got particle 1 constantly showing up. So what's happened here in this export is that we haven't updated the correspondences between all the frames. We also haven't included the correspondence trails, which will allow us to export the data and then see it in the Excel file. So here now in our Excel file, we have a number of columns saying particle 1 through several hundred. Okay, we see a lot of -1s indicating that that particle doesn't exist or wasn't found. And there we can go through and we can find a nice particle in this data that we want to track. So let's take this one for example. We can scroll all the way back up. We can see that it's particle 65. Okay. And so now what we want to do is we have our information for our tracking. And now we want to graph some of that information just like we showed in the PowerPoint presentation. So we can go to the particle menu and we can include the average speed in our plot. We can zoom in and with our mouse, so we'd have to just click on the graph to zoom in and zoom out. We can also set the bounds of the graph by clicking on this check mark and setting the boundaries however we like it. Here we'll put it at 340 with the minimum as 75. And we'll leave the Y as it alone. We'll hit refresh, and now we have a good understanding of how the particle speed, what the particle speeds are. And if we undergone an image calibration, we'd have this not just in pixels, which I can display this legend, refresh, and now I see my information in pixels per second. But had I gone through the calibration toolkit, I would actually have this in terms of meters per second or micrometers per second, whatever the units are for that would be shown here in this legend. And this is now defaulted to show, and we also have some additional features for particle where we'll have the X and Y velocities in this drop down box as well. So now what I want to do is I can adjust this and go up to the 2D tracking toolkit. I've already enabled this previously, and I've already added a feature using the add button. I'll just go into this box and I'll set this virtual point to be for, what was the value that we chose? We chose it to be particle 65. So we'll go in here, we'll set the virtual point to be correspondence 65. We'll hit apply, we'll close, apply and close. We'll maximize this window again and go back to our graph configuration box. We'll add that. We'll do the X, not the acceleration, but the X and Y velocities. Okay, now we can see the X and Y velocities for that particle, which it doesn't seem to be a very interesting particle at all. Right, it's not really doing too much. We can also change the color so we can get a slightly better contrast. Just confirm things. So now if I go to this notebook, I can go up to these higher number of particles. And I can see that particle 85 looks pretty good, so I'll try to reset the virtual point as particle 85. Another good one might be particle 87. Okay, now I see a pretty good plot of the speed over time. I can also go in and change that again and see if 87 is any better than that one. Apply, not convert, close. Fresh, and I can see information about that particle, and I'd have to go to that frame and analyze what's going on with that particle to understand what this plot is giving me. So with that, we've covered everything that was in the PowerPoint. Please let me know if you have any questions. You can just type it in the chat, and I'll handle those offline through an email that we'll send out later on in the week. Thank you for attending the webinar. Please send me your questions. If you want to email me, I will send you a link for my email, and we'll follow up with any questions offline. Thank you, and have a good day.